This is Philip Winston with Tobeva Software. I'm going to be talking about work I did on Napari last year during 2020. And what you're seeing right now is kind of the end product. This is the octree rendering a remote data set inside Napari. And you can see it's pulling down tiles and stitching them together. So we'll talk more about that. And I just wanted to say you can look on GitHub. Most of the, or at least a lot of the images I'm showing in the presentation are from PRs. I just grabbed them from PRs. And so if you want more details, and also I want to say we are looking for some people to jump in and help out with this code. I'm not going to be working on it as much this year, but I will still be involved, and I would really like to see a couple people jump in and see if we can move this from experimental to mainstream. My little tip of the day is YouTube. You can use JKL keys. I find it a lot easier than the slider for longer videos. So what is Napari? So I tell people it looks kind of like Photoshop, which I think is true. You have layers, you have images, but it's multidimensional. And so that really comes up in scientific context where you acquire tons of data with tons of different variables and you need to sort of slice it and dice it. And so what can we say about Napari? It's written in Python. It uses NumPy, which is totally essential to getting the performance. NumPy is a great library. And in fact, I think NumPy really makes Python viable for a lot of things. So it's really wonderful. Dask is kind of extending NumPy in many different directions for scalability, for processing, for multiple computers. Qt is the GUI we'll talk about. VisPy is a nice imaging library that's built on OpenGL. So these are the systems I interacted with. This is not everything. So what are we looking to do here? This is kind of what I was asked to do when I started. We don't want Napari to block. We want rendering to be fast and smooth. We want the user to be happy and productive. So I like to have in mind, who is the user? And I've worked with scientists before, so I have some idea. I kind of picture someone late at night plowing through their data, trying to get ready for a paper. And, you want them to have a good experience. You don't want them to crash. You want them to be productive. So that's kind of my model of the user here. So translating that into like what we're actually going to do, this is kind of what we came up with at the beginning. Add asynchronous rendering, add an octree spatial partition, add some infrastructure, and promote practices that are compatible with real-time rendering. So I'm coming from this background. I've worked on this stuff for really like 20 years. So I have a lot of ideas about what I've seen is successful. And so I wanted to communicate that, and hopefully Napari can adopt some of it. So these are the 4 things I worked on, really, 4 projects. They overlapped. And so we have perfmon, we have async is asynchronous rendering, we have the octree, which is built on asynchronous rendering, and we have webmon, which is kind of a side thing, although it came up in the context of the octree. So the first one is this perfmon. So when I started, I said, hey, we really want to quantify the performance problems we're seeing. And I really want to do that so I can claim victory when I solve something, right? I don't want to say, hey, it got a little faster. I want to have some numbers, and also I really needed it for debugging, as I'll show you. So this is how perfmon works. You have this config file. You tell it what methods you want to trace. They can be in VisPy. They can be anywhere. And it produces this trace file, which is JSON. And this format is not mine. This is from Chrome. So you take one of these JSON files and you drop it into Chrome, and it renders as a nice little timeline. So Chrome has a bunch of developer tools, and so does Firefox, built in. Really a tremendous amount of tools are inside your web browser. You might not know it. So these are 4 examples of traces that I grabbed from PRs, and I'm not going to go into really what these mean. I just want to show you that this produces interesting output and a variety of output. So in this case, we're doing some kind of load asynchronously, and yet I'm looking at what's going on in the draw threads, in the GUI thread. This one, I put in a ton of timers. I was trying to track something down, and so you can really see, this looks kind of like a flame graph and is really helpful. I find it really helpful. This one I'm showing, again, asynchronous loads, and I have highlighted, in this case, is 235 milliseconds for the load. This one is kind of the Shangri-La of rendering. So this one frame here is taking exactly 15 milliseconds, which means it's going at 60 hertz, this is beautiful to me. This is what you'd like to see all the time. I want to just talk about this for a little bit because I think this is a mindset that people don't always have. How would I debug the octree or the asynchronous loading without a tool like this? You'd be editing the code, you could run it in the debugger, you could look at logs, but none of those are going to work very well because so much is happening with real-time rendering. In a few milliseconds, hundreds of things can happen. And so I've been down this road, and it's very frustrating as a developer. You can spend hours in days and weeks sometimes trying to figure stuff out. And so there's a guy, Joshua Waitzkin, on the left here, who he styles himself as an expert on learning. He was a chess prodigy. The movie Searching for Bobby Fischer was made about him. And then he became a Tai Chi expert, and then he did foiling, all this stuff. And so he had a great point. What he said was, you can watch 1,000 hours of YouTube videos of people doing Tai Chi and fighting, and you're only going to learn so much. But if you get an opponent who hyperextends your elbow once, right, bends your elbow on purpose the way it's not supposed to be bent, you are going to learn, very, very quickly. And so I've kind of been down this road so many times that it really has sunk in that, hey, it's worth taking a couple weeks to write this tool. And so in the bottom, you see this is more the workflow that I'd like, right? So you run the tool, you make a change. You run the tool, you make a change. You run the tool, make a change. And really, A, it's more productive, but B, it's just more pleasant, right? Because nobody likes to be doing something with a tool that's not suited to the task. And so anyway, so I'm a big proponent of tools like this. And another usefulness of it is, here's a PR by someone else, not me, and they've got 6 perfmon plots. And so I love to see that. It's a lot easier than trying to describe the problem. So I really think tools like this are useful. So should you write a tool? I'll just say yes, but then I'll have some caveats. So man is productive based on the tools that he can make. And in software, the dynamic range of tools is actually even bigger than these 3 levels here, right? Because you can do a 4th and a 5th and a 6th level. And so that's really how big companies get things done, how open source gets things done is by writing tools, getting them solid, getting them in use, and then writing more tools. When should you not do it? Well, do you have the time? If I took 3 months to write perfmon, I wouldn't have had time to implement anything. Is it going to work? How much is it going to be used? Who's going to maintain it? How long will it be around? You shouldn't always dive in and write tools, but quite often it's helpful. The second thing is asynchronous rendering. And so this is enemy number 1. This is what you get if your program on Mac blocks, This was actually pretty easy to fix. So as soon as we introduced the chunk loader, that went away. But you have another problem, which is your frame rate. So you won't get the spinning ball if your frame rate is even as bad as 1 hertz. But 1 hertz is not really usable. I want to point out 3 things on this graph. One is, for our purposes, going faster than 60 hertz is not really helpful. So in VR and some games, you do want hundreds of hertz. But for us, I consider 60 hertz pretty much perfect. The other thing to point out, this is really important, as the frame rate falls, it's kind of like boiling the frog. Like nobody sounds the alarm because the software is still usable. And then one day it falls below 10 hertz and suddenly it goes from usable to just very unpleasant to use, close to impossible. That just keeps getting worse. If you're working on a product that has a rendering aspect, it's important to really be on top of the frame rate and try to keep it in the productive range. Why is anything slow here? What's slowing us down? We have this super flexible system where we render out of arrays or array-like objects. You're rendering an ND array, a NumPy array, which generally or always is in RAM, and that's fast. But there's other array-like objects, and one of them is a Dask array, and it's more of a mystery box, right? So behind that array access could be computation, it could be disk access, it could be, here I've got this map of the undersea cables of the internet. It could be anywhere. And that is a complication, but it's also where I think all the power and flexibility of Napari is going to come from. So I love Dask, and I think it's great. I just think it does present the challenge, but it actually was not too bad. Sort of do the asynchronous loading. We created this thing called the chunk loader. It actually was simpler than this. This is after the octree work, so this is a little more complicated. But this is not a class diagram. This is an object instance diagram. So Napari makes a chunk loader. It has a cache. It has a loader pool group. It has a bunch of loader pools. The loader pools have a delay queue. They have a thread pool. I'm not going to go into in detail except to say that it does work. And I would point out this delay queue is pretty neat. A lot of this stuff is really from previous systems that I worked on and ideas that are in the literature. But delay queue I have not seen very much, but I'll show you, the benefit of it in a second. First of all, here's kind of the life cycle. The layer needs data. Instead of loading the data, it makes a request to the chunk loader. The chunk loader loads it in a thread, passes it to this chunk receiver, which is just to transfer it over back to the GUI thread. And that's it. That cycle just gets repeated over and over again. That's asynchronous loading. Here it is, sort of in action. Here's 6 threads, and they're all hammering away, loading stuff. And at the top, you see the tiny, tiny little draw cycles because they are running unimpeded by the loads. In this case, I'm going to show you what the delay queue does. So the user is scrolling very rapidly through the slices, and most of these loads the results are being thrown away because we can't interrupt a load once it's fully in progress, and that's a threading issue. It's not a Napari issue. And so what we discovered is if we add a little delay, 100 millisecond delay, if the user's rapidly scrolling, then no loads happen. The user has so quickly changed from slice to slice that there's no point in even initiating the load. And then when they do stop, we load it. You could ask, well, was all the async work not needed? And it is needed in a bunch of different cases, including the octree. So the octree constantly uses the asynchronous loading. It was totally necessary. So for the octree, first of all, I'm really talking about a quadtree in most of my examples because that's all we have implemented, but the code is going to call it the octree because that's where we're heading. Octree just means a tree where every node has 8 children, and a quadtree is a tree where every node has 4 children. At each level, if you look at a tile, say on her eye, right, Mona Lisa's eye, if you look down at the lower level, that one tile translates to 4 children. So that's where the quad tree comes from. We don't actually build the trees usually, but I'll just show you. So here, we broke the image into tiles, and then we take 4 tiles and combine them into one, but then we downsize it to the size of a tile. We do that again. So this is a little pyramid with 3 levels. I'll even show, we take that level 0 tiles, there it is. We take level 1, and we take level 2. And the thing to note is on the left, all of the tiles are the same size because I'm drawing them on pixels. But on the right, they're different sizes because we're drawing sort of the physical size or the size they need to be. That level 2 tile is the entire picture. So now we'll show how you render it, showing sort of 3 zoom levels. What you see is in the top, we only need to draw the 1 tile. In the middle, we draw 4 tiles from kind of the middle level. At the bottom, we draw, again, just 4 tiles. So that's the whole key. Anywhere you look in the image, some of our images have 35 million tiles in the base level. But anywhere you look, in this case, we're drawing 4 tiles. In reality, we draw maybe 20 tiles. You have 35 million tiles. We just need to draw 20 of them. Now, of course, we don't put those white lines. I do have red lines for debug, but when you turn off all the lines, it really looks pretty seamless. Here on the right, we're visualizing which tiles are being drawn. The tiles that are being drawn are in red, and the yellow is sort of the view frustum. It's moving around the screen, and you see wherever it is, wherever you last look for your keys, that's where they are. So, wherever you're looking, we draw the tiles necessary. Now I'll show the same thing, but here we're going to switch octree levels. So as you zoom out, you're now drawing more and more of the picture, so you can use bigger and bigger tiles. So again, wherever we are, you're drawing, in this case, maybe 20 tiles. This is the only code in the presentation. I just felt like I had to have a little bit of code. So I mentioned that level 0 sometimes has 30 million tiles, right? We can't afford to even have blank spaces for all those tiles. So instead, every level of the octree just has a dictionary. And if you ask for a chunk, we basically say, yeah, if it's in our dictionary, then you can have it. Otherwise, optionally, you can create it. And so this, again, is kind of like wherever you look, there are chunks, but only because we create them on the fly. And the benefit of this is here, I think this is the data set with 35 million tiles or a similar amount. And on the left, it's the same tile view. So it looks like we're kind of drawing or painting with gray, but those are just tiles. They're just really, really small. And this is exactly what you want, right? You only want to be allocating space and time where you're actually looking. This is kind of the octree data structure. There's two parts to it. There's the data itself, which is NumPy arrays or Dask arrays, and then there's the levels. So each level just has a little dictionary of the chunks that are currently being viewed. So typically at most 20 or 30 chunks. Let's just look at two details of that. So one is the chunks don't store the data, they just point to the data. And so that is good, that is efficient. And then the second thing is, well, where's the tree here? I don't see a tree. We're talking about a quadtree and an octree. Well, the tree is really just in the code, and the code, you can do things like get the children for a node, or get the parent, or get the ancestors. And we know how to essentially hop around in the levels. And so that's where the tree is. So it's a little bit conceptual, but it works really well and it's very efficient. So how do we render this thing? We had to implement something which is pretty standard in computer graphics, but it's a little bit tricky, which is this texture atlas. You can look up online, or you can look in our GitHub. There's information. But basically a texture atlas is a big texture that stores a bunch of little tiles. I want to point out here, you can see the tiles are different resolutions because they're from different levels of the octree. When we go to draw it, you have to draw from all over, right? So this looks complicated, but actually this is incredibly simple and efficient because the graphics card does this in its sleep. It really is super easy for the card. And so you basically just send it these quads and you tell it where to pull the textures from, and it works really well. It's very common in computer graphics. So this is the whole thing, right? So on the left is the visual we just saw. In the middle, there's a layer, an octree image layer. And inside there is the octree, and then we already saw the chunk loader. And so these three pieces just work together. The octree loader is actually the most complicated thing. I'm not going to try to diagram how it works because I think it's probably going to change. I will show what it does. So the loader is loading chunks that it needs, and it's choosing what level to draw. This is a good screen capture. It shows kind of what's going on. On the left side, it looks like a little strip of data, but actually that's a very big square, a big tile that's several levels up in the quadtree. That's why it's so pixelated like that. And so that's going to be quickly replaced by higher resolution tiles. These smaller tiles are either on their way in or on their way out. It depends whether we're zooming in or out. But basically, this is a transition point, and you will soon end up with what I call the ideal tiles. So the ideal tiles are the ones that match the screen resolution the best. In this last case, again, we have a really big tile you can kind of see below, but then we have 4 sort of high-res insets. And this is a feature that I did not have in a tiled viewer I wrote a number of years ago, and I really like it because it means we're using what I like to say, we're just drawing with the best available data at all times. That was the octree. So now is webmon. So webmon is something we kind of backed into or stumbled into that I think has a lot of potential, but it's also potentially just, a prototype. We'll see. So here is my estimate of how done these things are. So maybe perfmon is 80% done and async is 80% done. Octree is 50% done, maybe less because we have to do 3D. Webmon is very generously 10% done, so it's just starting. So where did this idea come from? This is important. This is like the genesis story. I spent a couple weeks writing this UI in Qt that was specific to octree rendering, and it displayed the tiles, and it had a bunch of controls. And I really found that using Qt for this was cumbersome, and then more so, it slows down Napari. It just didn't fit really with the UI, and so I did a little research on Qt. So it was released V1 in 1996, which is right after I graduated from college. And so you might think I'm going to say, well, if it's old, then it's not good. But Linux version 2 was released in 1996, and it's incredibly, it's arguably the best operating system today. So it's not the case that old is bad, but let's see what was going on then. So this is apple.com in 1997. So you can see the web was just getting started. So what I'm proposing is, let's use, web UI. So on the right, I already showed this, but this is Chrome, right? So on the left is Napari, and on the right is Chrome. Chrome is pointing to Napari, essentially. It's pointing to a plugin. And, this is pretty wild. So Chrome is using WebSockets here. It's got essentially a live connection. I think pretty arguably the Chrome display is smoother than the Napari one. So this is pretty nice proof of concept that you can kind of combine these two environments. So how does it work? I would just say, Napari shares out some memory. We have a plugin that launches that connects to the shared memory, and then it itself is a web server, and then you connect to the web server. The nice thing about using shared memory is you could have other clients that are not web-based, or you could have, if someone wanted to fork the web UI, you could have two different web UIs, but both connecting to one Napari. So it's really flexible and powerful. This could be a text interface, if you didn't like the web one. So here's a possibility, right? So today you have VizPy, Qt, OpenGL. Maybe someday you could have, React or any other web framework, DeckGL or any other Viz library in WebGL. I'm going to belabor this a little bit because I just really want to make, the point. So Qt came out in 1996. Google was founded in 1998. Facebook in 2004. Twitter and AWS in 2006. So these four companies, the current market cap is $3.8 trillion. So that's a lot of incentive for people to work on web stuff. So in 2011, you've got WebGL, 2013, React, 2016, DeckGL and Vega Lite, 2017, Tailwind. And so what I would say about that is, to me, these all feel brand new. I mean, I've been doing this for a while. So Vega Lite and Tailwind, I really found out about, 3 months ago. They all seem brand new to me, but they're 4 years old, right? So even the youngest thing here is 4 years old. That's college, right? That's not a short period of time. So what am I really saying about webmon? Should Napari have used a web UI from day one? I'm going to say no, because one, that was a couple years ago, and two, it'll be a challenge to do the interactivity and the quality from web. But should Napari pursue this possibility? I will say yes. All right. So I think it's pretty clear it at least has to be pursued and kind of entertained until it becomes viable. Like, I think it's just a question of time. So can a web UI fully replace Qt VizPy? I don't know the answer to that, although I think it's really a question of time. So in 10 years, certainly. In 5 years, probably. I don't know, about 3 years, 2 years, 1 year. So that's where it goes. So the code that I've been talking about that I wrote during 2020 is listed here. You can pause and look at this. I will say that the last three projects, async, octree, and webmon, are experimental. So we invented this category of code called an experimental. And it's not just a label. It actually means that if Napari starts without one of those feature flags, it will not even import and certainly not run the code. That means even if there's a horrible bug in the experimental code, it won't affect mainstream Napari. So I really like that model. I think other projects do something similar. So the feature flag idea has been around for a long time, but it's gotten a lot more popular in the last few years with cloud computing. And so what is a feature flag? So in this case, let's say today you have a code branch and you have two flavors of your code, A and B. Now, when you release that code, you've got to choose which to release. Now, you could have a separate release channel, like a beta channel, but same thing there, right? You have to pick which branch you're delivering. So a feature flag means both features, both code paths are implemented in the same code base. And when you release it, you release both. Now, a lot of people object at this point and they say, hey, you're going to replace Git branches with feature flags. And the answer is no, you actually use both. Okay, so that's what we did. By both, what I mean is Napari includes mainstream Napari and it includes the octree. And then when I make a PR, That's a branch, and that includes mainstream Napari and a new version of the octree, right? And so when you make a release, you have to, again, choose which branch. And so this is, in my mind, the best of both worlds. Now, I still strongly condone branches alone for many cases, but if you want the user to be able to have access to the code, a feature flag, I think, is the way to go. And then you also use branches. So that's it. This is the 2020 rendering update for Napari. Feel free to get in touch with me on Zulip or on GitHub or on email. And thanks a lot for watching. And now I'm going to show some footage of the octree rendering some art. So I'll give a couple minutes of that and you can just enjoy that. Thanks again. Bye.